Thank you, everyone. I've spoken at this conference a number of years, but this is the first time I've had the opportunity to do a keynote, so this is a great honor. Let me plug this in so my slides will work correctly. All right. So what I want to talk about today is a problem that all architects have, is trade-off analysis. And this is really the essence of software architecture, in my opinion. Software architecture is not really about finding magic bullet solutions to problems, because they, of course, don't exist, or if they did, they're quite rare. Instead, your best job as an architect is being able to objectively analyze trade-offs, because that's the job. There are few problems that we run into that have nice, clean, simple, elegant solutions. And this is something that we've been thinking about a long time in the software world, so much so that if you start doing research on this subject, you'll run into some things like this. ATAM, the Architecture Trade-off Analysis Method, or there's a similar one called CBAM, the Cost-Benefit Analysis Method. For some reason, all of these trade-off frameworks are so complex, they need four-letter acronyms, not just three-letter acronyms. But this was developed by the Carnegie Mellon Institute, Software Engineering Institute, Carnegie Mellon. Sounds very promising, and its purpose is to figure out the trade-offs that you're dealing with in software architecture. Here are the steps in ATAM, and I'm not going to go into a lot of detail about this because, as you could probably guess, this does not work at all anymore. And in fact, let me filter this down to the things that are still useful in this list. Well, they had a visual artifact that's kind of useful now, but the problem with this, of course, is it's a giant, long, bureaucratic method that assumes that you can take all sorts of people away from their day job for a week at a time to have these discussions about software architecture and trade-offs, and then take months to make decisions about this, which presumably you then drop through a hole in the floor and developers do something with it. So definitely not something that is realistic or desirable in this day and age. This gets back to something that we coined in our first book. When we were writing the Fundamentals of Software Architecture book, we were looking for things that seemed universally true across software architecture. And we were hoping to find like 10 of these things, and we ended up finding 2 of them, which we coined as the laws of software architecture. And the first one is that everything in software architecture is a trade-off. In fact, one of the ways you can think about what is a software architecture decision, it's a decision where all of the options have significant trade-offs attached. That's one of the ways to define software architecture. But we also had a corollary to this law, that if you think you found something that isn't a trade-off, it just means you haven't identified what that trade-off is yet. And I'll actually show you a concrete example of that, a common mistake that a lot of organizations make around failing to do trade-off analysis and failing to identify that, oh, maybe we just haven't discovered this thing yet. So when Mark and I were writing the Fundamentals of Software Architecture book, we kept bumping into these problems that we wanted to write about, but as you started digging into them, they got more and more complicated, and we had to give up on it. And we said, you know what, we're just going to kind of push those into a pile of things that were too difficult to deal with in the Fundamentals book. And in fact, we were on a call at one point, and Mark said, as we were ejecting yet another one of these topics from our Fundamentals book, wow, we should call our next book Architecture, the Hard Parts. And in fact, once we got finished with our Fundamentals book, we started looking at this now giant pile of difficult problems and started poking at them, saying, why are you so difficult? That, of course, led to this book, Software Architecture, the Hard Parts. And you'll notice the subtitle of this book, Modern Trade-off Analysis for Distributed Architectures, because it turns out that was the problem with all of those difficult problems. The thing they had in common was that there were no real solutions. There were just ways to analyze trade-offs. One of the things that Mark and I like to say, as software architects, we're not trying to achieve the best, because best implies that everything is as good as it could be. Instead, what we're often trying to achieve is the least worst. What's the least worst combination of these trade-offs that we can get to work and make this whole thing function in a reasonable way? Now, after Software Architecture, the Hard Parts, we undertook this adventure that just came out, which is Head First Software Architecture. If you're familiar with the Head First books, it's almost like a graphic novel, very, very cumbersome to write, as it turns out, but much more sort of an intro guide to software architecture than even our Fundamentals book was. And A great example of that is one of the questions that we very specifically tried to avoid in our Fundamentals of Software Architecture book is, what is the difference between design and architecture? Because it's just one of those tar pits of never-ending argument and who knows and nuance, et cetera. But in Head First, we felt compelled to really address that question. And that seems like a relevant question at a conference named Domain-Driven Design, to talk about what the difference between architecture and design is. So let's talk a little bit about architecture versus design, and then we'll come back to trade-off analysis in software architecture and why you can't treat them the same. So like many things in software architecture, it's not a binary as to whether you are architecture versus design, but rather a sort of a messy spectrum of where do you fall in this spectrum between architecture versus design. But there's some criteria that pulls you toward one side versus the other. And we separate these with 4 letters. We actually do this as an exercise in some of our classes. Architecture decisions tend to be strategic, whereas design decisions tend to be more tactical. Strategic meaning this is a long-term decision that is going to affect a lot of things. In other words, significant trade-offs associated with this decision, whereas tactical things, a lot less important trade-offs associated with those kind of decisions. Typically, architecture decisions require high effort to change that decision. If I choose a particular architecture style, it is a very large effort to change to another architecture style. If I change something about user interface, it's fairly trivial to change it to something else. So architecture versus design. And then finally, architecture decisions are ones that have significant trade-offs associated with it. And design, well, I don't want to use insignificant, but less significant trade-offs associated with tactical or design kinds of decisions. And so one of the things you have to decide as an architect is it more about architecture or design? So we're considering using microservices for the new system. That's very much an architecture level decision because it affects pretty much every aspect of the system. It affects deployment, the way you do deployment, it affects design, it affects capabilities. Pretty much everything data is affected hugely by that. We need to move the cancel button to the bottom of the screen. Obviously a trivial thing to do, and you can do that in just a few minutes. But a lot of these decisions are a whole lot more nuanced. We're considering breaking the single payment service into separate services, one for each payment type. Now, this gets to one of the perpetual problems we have in software architecture is its philosophy versus engineering. So what is the correct granularity for service in microservices? Well, it's supposed to be single purpose. Okay, great. That's a great philosophy, but what does single purpose mean? Are all notifications single purpose? Or are all customer notifications single purpose? Or is each kind of customer notification single purpose? Because I could argue over drinks, any one of those as being singular enough to be single purpose. So we need something more than just philosophy to help us with engineering tasks like this. One of the questions we frequently get, and this goes to the heart of architecture versus design, is, well, why do you need architecture at all? Why don't you just start and then emerge the architecture over time? Turns out you can't do that. Because of this. So one of the common arguments you get is if you're designing some new thing, let's say you're trying to design something like a lorry, you shouldn't start by trying to design a lorry. What you should do instead is start with a roller skate, and then a unicycle, and then a bicycle, and then a motorcycle, and then a car, and then a lorry. You merge the design as you go, figuring out how things are supposed to work as you go. And this is great in the design world, because design is about behavior. And you can't emerge behavior over time as you're building something. But you can't do that with architecture. Because a roller skate doesn't support the same kind of capabilities a lorry supports. You can't start with a roller skate and build enough extra stuff on it to support the same level of weight and velocity and speed, et cetera, that a lorry has. Because design is about behavior of the system. But software architecture is about capabilities of the system. You've always heard software architecture characteristics called the ilities of software architecture. It's because they describe capabilities. And you can't emerge capabilities, but you can evolve them. So many years ago, I was doing a talk where I was calling emergent architecture and design, and it was one of the first iterations of that talk. And my colleague, the person who's doing the keynote tomorrow morning, in fact, Rebecca Parsons, took me aside and gently but forcefully explained to me that there is no such thing as an emergent architecture for exactly these reasons. You can't have an evolutionary architecture, and that's what she's going to focus on tomorrow morning, but you can't have an emergent architecture for exactly these reasons. You can't emerge capabilities. They require at least some level of upfront planning. But again, the amount of planning you do is really contingent upon how complicated the thing that you are building is. And in fact, we identify 3 different things: an adaptable architecture, which is an architecture that allows incremental addition while maintaining existing functionality. That's taking something that works and gradually adding more onto it, which works for a while but becomes an anti-pattern because you can't support all the things. An evolutionary architecture is one that supports guided incremental change across multiple dimensions. That's what Rebecca will be talking about tomorrow morning. An emergent design is a design that gradually emerges as understanding of the domain deepens and broadens. This is why there's a separation here between evolutionary architecture and emergent design. But you often hear this trope, that's the definition of agile, is no architecture or any kind of pesky planning like that. We should just start getting to work on stuff. And that will actually work in some systems, but let me go back to a building analogy. So if I need to build a doghouse for my pet, I don't need architecture. I need lumber and a hammer, and I'll just nail it together and it'll be fine. If I'm designing a 50-story office building, I've got to do planning. I need elevators and stairwells and safety and all these other concerns because there's lots of different serious trade-offs to consider there. If I'm building a little simple website to track like a kid's football team registration or something, I don't need an architecture. I need to download some sort of framework and just kind of piece it together. But if I'm trying to build a highly available, highly scalable bidding site online with all these constraints and trade-offs, I've got to do some planning. It has to require some architecture. So, and this doesn't mean, Agile doesn't mean no architecture. Agile doesn't like formality, but the thing that Agile really likes, the real core of Agile software development, is fast feedback loops. That's what we need to do Agile architecture. It's not the absence of architecture, which is the absence of planning, but the ability to make plans and then feedback on those as quickly as we can to see, are we going in the right direction? This is very commonly, when you're going someplace you've never been before, which brand new applications are, the faster the feedback you get, the faster you can course correct, which is also true in software architecture. So let me give you an example of this from our Software Architecture, the Hard Parts book. And it's one of the trickiest things that teams, particularly new teams to microservices, fall into, is what is the correct granularity for my service? We talked about the philosophical argument here, but philosophy doesn't get you very far. What we need are tools. So the way that I picture this metaphor for architects is that you have a toolbox. So all of you have seen some craftsperson come to your house to work on electricity or plumbing, and they have a toolbox, and you probably peered inside out of curiosity, and they have standard tools like screwdrivers and wrenches, but they also have exotic tools in there, mysterious tools that have special purposes that only they really understand and know about, but sometimes you need really specialized tools. That's you as a software architect. There's some standard tools like wrenches and screwdrivers, but they're also really highly specialized tool for your organization that only matter there, they matter a lot. So what I'm going to do is give you a starter kit for generic tools, but you are encouraged to go add more to that toolbox as you discover these things within your organization. So what I'm going to describe here are 2 kinds of tools for granularity: disintegrators, which are forces that encourage you to break things down into smaller pieces, and integrators, which encourage you to bundle them back together. I have 5 disintegrators and 3 integrators. Here's the first of the disintegrators, which is probably the most obvious one, service functionality. I want to break it down by its behavior. So for example, if I have a notification service with text, email, and postal letter, I might break that down into SMS, email, and postal letter. Seems like an obvious way to break these down. However, one of the metaphors we use for these disintegrators is sort of like in physics, you have the strong nuclear force and the weak nuclear force. The weak nuclear force does stuff except when the strong nuclear force dominates it and does other stuff. This is why our universe works the way it does, is the interaction between those forces. And these disintegrators are sort of like the weak nuclear force as well, where domain concepts are the strong nuclear force. For example, let's say that I have this customer service that has these characteristics of customer in it, profile, references, and comments. If I disintegrate that into 3 individual services, this does not mean that I am now building something that are preferences for the entire organization for everything that needs preferences, or comments for everything that needs comments. I'm not trying to turn my architecture inside out. This would still be customer preferences and customer comments and customer profile. In other words, that domain binding of customer-ness is the strong nuclear force, and the disintegrator is the weak nuclear force, which is another way of saying don't follow these forces and cause you to do something that's not smart. The second of these has nothing to do with behavior at all, but rather volatility of your code. So let's say that I have a notification service with SMS, email, and postal letter, and code almost never changes in the SMS and the text and email, but because of weird laws about postal letters that travel across state lines, we have to constantly tweak the postal letter code, and so it's changing all the time, and it's quite volatile. So one way I might think about disintegrating that is around the stuff that hardly ever changes and the stuff that changes all the time. 2 things I typically say parenthetically at this point. And the first is this. You may have heard of this little mini cult in the software architecture world right now called volatility-based decomposition. And there are proponents of this that say that's the only thing you should ever look at is the volatility of the churn of your code. But that's not true. That's just one of our disintegrators. And in some organizations, there's a clear distinction to be made by looking just at volatility, but it's not a universal truth, and it's not the only tool you should use. But the other observation I'll make about this is the example I alluded to earlier of the common trade-off that most organizations miss. I get approached by a lot of organizations that say, essentially, well, we really love this idea of microservices and really tight, bounded context, the ability to do really fast change because everything is so decoupled. We love this decoupled architecture idea. But as we build it, we also want to achieve a high degree of institutional reuse because we don't want to rewrite a lot of stuff. So as we build assets, we want to be able to reuse those things as aggressively as possible. And I have to break the bad news to them. I'm sorry, but reuse is by definition coupling. That's kind of how you implement reuse, is by coupling to stuff. So you cannot have highly decoupled architecture and a high degree of reuse at the same time because they are fundamentally incompatible. One of the reasons you hear the mantra that duplication is preferable to coupling in the microservices world because both of them are bad. Which one is least bad is the question you always have to answer as an architect. And this goes to the trade-off that everybody misses. To effectively reuse something in software architecture, there are 2 things you have to look at. And everybody gets the first one right, and everybody misses the second one. The first one is abstraction. Oh, look, I could use this from a bunch of different places. It's the same abstraction. I should extract that and reuse it, which is true. But the second really critical piece is low volatility. Because if that thing you've reused has high volatility, it's going to drive churn in your architecture. Because every time that thing changes, everybody else has got to stop and coordinate around that change. Even if you're not broken, you have to still test and check to see if that change has broken you. And so in this scenario, letter would be a terrible candidate for reuse because we'd be constantly having to adjust and churn around it, which is why the most effective reuse we get in software architecture is plumbing. Frameworks and libraries and technical things, not domain concepts. And this is why domain concepts are terrible candidates for reuse, because what's changing the fastest in your application? The thing we're writing the application about, which is your problem domain. So this is part of the encouragement you always hear in the design world. This is the architectural reinforcement that, yes, in fact, you should keep volatile things tightly encapsulated within your ecosystem. The third of these disintegrators is scalability and throughput, which is sort of a shorthand for this operational family of characteristics: scalability, throughput, performance, et cetera. For example, let's say I have my notification service, text, email, and postal letter. I get 220,000 texts a minute, 500 emails, and 1 postal letter. I could split this down into text, email, and postal letter. But I might notice here that, well, the magnitude of email and letter are practically the same there, and they're a rounding error compared to the SMS thing, so maybe I should just bundle those two together into a single service. Okay, we could do that. What are you going to call it? Non-SMS messages? That seems bad to name it for what it's not. I mean, it didn't do anything wrong. Naming things is hard in software. So again, the strong nuclear force of common sense would keep you from trying to bundle those things together just because they have similar characteristics, and you probably leave it as 3 services just because you don't want to have to explain at some future date of what something like a non-electronic email and letter correspondence service is, or some crazy thing like that that would grow out of that decision. The fourth of these is fault tolerance, which is the special family of operational characteristics around availability, reliability, and integrity, data integrity, et cetera. For example, if I have a single service and I have misbehaving code in that single service that is prone to throw critical stack traces and take down the entire thing, obviously when that happens, it takes down the entire process. And I can isolate that by separating those into separate services so that if one of them does go up, then I've got recourse. I can do tricks in the operations world like service discovery and circuit breakers, et cetera, to mitigate this problem. But by separating these, I separate the problem service from the other ones. Then finally, access restriction. Again, a pretty obvious one: security and concern about privacy. For example, if I have a profile service that has some sensitive information, either private information or financial information, I may want to split those so I can have stronger security around one service versus the other. So those are all disintegrators, forces that encourage you to break things down into smaller and smaller pieces. But let's look at the opposing force, which are integrators. And it seems like developers really attack the disintegrators with great relish and gusto, but are more reluctant for the integrators. Let's see why that might be. The first of these is something else you've also heard about microservices, is try to avoid doing transactions across services. So if I have a scenario here where I have a service that shares information with another service, and I want to make sure that is shared atomically between those two services, that means I'm trying to do an ACID transaction across two services, which is frowned upon. It's not impossible. In fact, this is basically the second half of software architecture, the hard parts, is how to do this. But the preferred way of handling this is to say, okay, well, I've broken this down too far. Maybe the solution to this problem is just bundle it back up into a single service. And this is a great illustration of this kind of iterative design within software architecture, because you break down a service by using the service functionality disintegrator, but then you realize, oh no, that's going to force me to do transactions, and so you bundle it back together. Maybe use a different disintegrator like volatility or scalability and throughput to break it down. Let me just parenthetically give you one of my favorite tips for software architects and really anyone working on diagrams in software architecture. I'm a huge fan. So every good drawing tool for technical diagrams has this concept of layers. And most people use layers cosmetically, but I use them semantically. The bottommost layer of all my diagrams is always lines and boxes, with solid lines being synchronous communication, dotted lines being asynchronous communication, and database cylinders. And then I build a layer on top of that that tells me what protocols I'm using. Is it events and messages, etc. I can put another layer on top of that that shows me where do I think my bounded context exists across the physical topology of my architecture. And another layer I almost always create is where are transactional boundaries within this architecture. And what's nice about that is you can turn layers on and off and see where transactionality and bounded context overlap, where things like service topologies and communications overlap. So it gives you a way of using the same diagram with multiple views on it to learn, to analyze your architecture. The second of these, data dependencies by integrators. This is a tricky thing in microservices because one of the unique things about microservices, because of that bounded context philosophy, is you have data fidelity at the service level. And so maybe I have a single service with 3 functions in it, but in the real world, it would probably be more like this, with some mappings to a relational database, or maybe a different kind of database. And my desire is to use the service functionality disintegrator to break this down into 3 smaller services. But, of course, I have data dependencies as well. I could do this, which is worse than what I started with, because now I have all the latency and overhead of microservices, but none of the advantages of independent scalability or decoupling, because they're all coupled to each other at the data level. So this is not in any way better. In fact, it's markedly, objectively worse. And so I really want to match up the tables along with the services. So this is kind of like the matching game you played as a kid where you slide tiles around. But here's the problem. Function A writes to 1, 2, 4, and 6 and reads from 5. B writes to 3 and reads from 2 and 5. And C writes to 5 and reads from 1, 2, and 3. Well, if you follow the philosophy that the service that writes to it owns the table, then A gets 1, 2, 4, and 6, B gets 3, and C gets 5. But I got all these read access stuff left over. What am I going to do about that? Well, I could do this. This is officially the worst possible solution to this problem. These are all the disadvantages of microservices and 0 of the advantages of microservices. So this is officially a distributed ball of mud, which you do not want to do. Now, there are techniques that you can use to untangle this mess. In-process caching is used a lot. Have a service at startup load information into its cache, and so read it from there directly is one common solution to this problem. But the other common solution is just don't break it down. Problem solved. This is a really common outcome where overzealous developers slam into a wall of data dependencies and have to bundle things into bigger pieces than you would normally like to, because as you've probably discovered as well, database developers do not think this way of highly decoupled databases. In fact, they've been trained since they were little tiny database developers that that's not the way data is supposed to work, and there are impassioned discussions to be had with them about that topic. Last of these is workflow and choreography. So let's say I have a single service and I've decided it's doing too much. We need to break it down using the service functionality disintegrator. So let's break it down into 4 different services. The problem is The reason it was one service to begin with is because it's doing some useful work. There's a workflow involved in this thing. And if I break it down into separate services, now I translate that workflow into network calls instead of just in-process method calls, which is way slower than doing it in process or in container. And responsiveness and performance is the bad surprise that a lot of teams get is when they go early into microservices, because let's say the original service here gave you some sort of SLA like 1500 milliseconds, but now when I call this, because of data fidelity, now I've got to hop and call this one and then call this one and then aggregate and compose and bring back to this one and then do some filtering, et cetera, and now significantly slower. This is part of the problem you often hear in microservices is performance can be an issue here, and this is exactly why. But you also have to worry about reliability and data consistency, because if I try to make this call and one of these services is down, there are patterns that I can use to mitigate this, but it's still something that I have to worry about. And so maybe the solution is just bundle it back together into a single service. This is a great example of how reactionary the software architecture world is, because I guess probably about 9 months ago, Amazon released a blog that said, you know, we tried building this part of AWS using step functions and realized it was too slow, so we bundled it back together into a single service. And the internet just went crazy. Amazon has abandoned microservices and gone back to the monolith. It's like, no, they haven't. They just applied this integrator, which is really common in architecture. Oh, we went too fine-grained, and now we have performance and latency and other headaches. Let's go back together, and those things go away. So Amazon has not abandoned microservices because they changed the granularity of one of their services, I think we can safely say. I want to stress that this is a beginner set of these things, but there are a bunch of these at your organization around all kinds of things, team, topologies, geography, problem domain. Look for these and start adding them to your toolbox, because this gives you an objective way to work on things like granularity to arrive at, if not the best granularity, then at least the least worst granularity. So let's look at a typical trade-off analysis that a modern software architect does. And the punchline here is we build lots of matrices. So this is an event-driven architecture, not necessarily microservices, but here's the trade-off I have to figure out. So I have this workflow with order placement and payment and inventory. Now the question is, should order placement query the database and hydrate all the information I need for order payment into a single contract, pass that contract first to payment and then to inventory, and then get those results back and write it back to the database? So that's one option I have, is a fully hydrated contract. The other option I have is, should I just go and query the database and grab just the key? Pass the key to the payment service, and it can then query the database to get all the relevant information. Say, for inventory, it can query the database, and then they will write their results back into the database directly. Which is better? Well, the answer to everything in software architecture is it depends. But what we now have to do as software architects is answer the inevitable follow-up question, depends on what? Okay, great. Now I've got to figure something out. But now let's see what it depends on. So first of all, scalability and performance. If I hydrate the entire contract, I'm going to get better scalability and performance, because the potential bottleneck here is the database. And in this solution, I only hit the database once to read it and then once again to write it back. And so definitely better for scalability and performance with a hydrated contract. But now I've got contract management and versioning to have to deal with. One of the fallacies that Mark and I have come up with in microservice architectures is that versioning is easy, because it's not. It seems like, oh, that's an easy solution, but now what's your deprecation strategy? Is it per service? Is it for the entire system? How long do you keep versions alive? How many versions do you support? Because there's going to be inertia for changing those things, so lots of complexity that ends up there. But there's another problem that ends up here that I want to focus on a little bit, because this is a constant mistake I see modern architects making. It's a very old problem with a new face. It's called stamp coupling. If you look at the Wikipedia page on coupling, it shows this ancient diagram from the book Structured Design by Constantine and Jordan. It's ancient because the thing on the far left, your programming language won't even let you do anymore. That's why you have things like private and protected and scoping in programming languages. But the one next to the last, stamp coupling, is still alive and well, and I'll show you how it manifests. This was actually named from the COBOL days, when data structures changed so infrequently that they'd get physical rubber stamps made to represent a particular data structure, and when a problem come along, they'd say, okay, which data structure is this? Okay, stamp onto that, and that's the data structure you used. But inevitably, because those things never changed, they would just add more onto it over time, and that's really where this name comes from. And the implication, here's what it looks like in the modern world. Let's say I have a profile service that has all this customer profile demographic information in it. And I have a wish list service that has everything I need to know about wish list except the name because it's owned by profile. And so I have an inner service call from wish list to say, hey, give me profile information. And I've wired this together in what we call a strict contract using JSON schema that just wires all these fields back and returns them all over here to wish list. Which is fine because wish list can now extract the name from it and get the name that it wants. This is stamp coupling, and here's why this is a problem. Let's say that at some point somebody comes to you and says, hey, I notice they have state in customer profile. Is that the full name of the state or is it the two-letter state code? Oh, yeah, you're right, that's ambiguous. It really should be the two-letter state code, which means I've changed the profile service and now broken the interaction between these two. Even though wish list doesn't care anything about states or state codes or any of that stuff, this is a really common fault that developers make in microservice ecosystems is over-specifying contracts because it's easy. The protocol just says, I'll just wire all the fields and I'm sure we'll need them at some point. But what we're doing when we do this is creating a more brittle architecture. That one change that shouldn't break anything is now rippling out and breaking a bunch of stuff. That is a stamp coupling. And that's a problem with this fully hydrated contract because payment's going to use part of it and inventory is going to use the other part and they're subject to changes. And then finally, we have multiple systems of record, which what if somebody else has changed the record in the database while we're doing all this hydrated contract stuff? So that's a problem. So what about key only? Definitely not as good in terms of scalability and performance. We're going to take a much slower because we're hitting the database a lot in this operation. But single system of record, no data consistency problems. I don't have to worry about stamp coupling or bandwidth or contract management stuff, which is nice. And so here's the actual trade-off analysis. You can go to your stakeholders now and say, okay, how scalable does this thing need to be? And if it's not much, then I have a much better solution. If it really needs extreme scalability, then I'm going to have to figure out solutions to those problems. This is the reality of modern software architectures. You have to do this trade-off analysis over and over again. And it's not like you can even choose this one time and say we're going to do that forever because different situations have different trade-off analysis. And let me show you what I mean by that. We end our hard parts book with a chapter called Build Your Own Trade-Off Analysis, where the entire first 14 chapters of the book are written in first or third person, but the last chapter in our book is written in second person. Because what we really do throughout the book is show you how to do trade-off analysis, and at the end we give you some tips about the techniques that we've been using so that you can use them themselves. And this is important in software architecture because one of the widely disparaged terms now in the software world is best practice. And think about that in terms of software architecture, a best practice, which does not exist. What that means is that every time this situation comes up, I can just turn my brain off and always do this thing because it's the best practice. It's not even a better practice, which would give me a little wiggle room. It's the best practice, and so no arguments allowed. It is the best. But you just can't turn your brain off for problems like that in software architecture because you always have to evaluate trade-offs over and over. And even for situations that you've already done it for, the variables always shift and change every time you make these decisions, and so you're constantly having to do this. But I showed you an example of doing a trade-off analysis, but this does not exist in a vacuum. It cannot exist in a vacuum. There has to be an end result of this trade-off analysis, and that has to reconcile back to the business, the stakeholders for the organization. So friendly people like this stock photo come up with decisions in organizations, and they decide time to market is our most important business driver. Now an architect analyzes architecture characteristics of the problem, and they translate time to market into capabilities like maintainability, deployability, and testability. Now, when we do trade-off analysis, we know what the target is. We do the trade-off analysis and yield results like performance versus maintainability. Okay, that's the trade-off we're interested in. That now maps back to the architecture characteristics we're interested in, maintainability, which maps back to the problem statement, which is time to market. So the outcome of this trade-off analysis in this case would be maintainability, because that's the thing that matches what our business driver is. So let's look at some examples of some traps to watch out for in this world. And the first one is the out of context trap. We have an architect that says, you know, I can't decide whether to use shared libraries or shared services for the common functionality in this system. Shared services, you compile it into the services at compile time, and they just run. A shared service, we call them at runtime to reconcile it. Which do I use? Well, what you do is a trade-off analysis. The real skill within an organization of an architect is figuring out exactly what this list looks like, of what are we really trading off in our organization when we make these decisions. But once we come up with this list, we can now do a trade-off analysis. If I have different kinds of platforms, then a shared code is going to be tricky because I have to have multiple versions of it, whereas shared service, I just call it, which is great. If I have high code volatility, having a shared library is going to be hard, because now every time it changes I have to recompile, whereas for the shared service I just call it and I get the new version of it, which is kind of nice. Easier to version changes with the shared library because I have a compile time binding and I know exactly what that version is. Now I've got to reconcile this at runtime with the service, which is tricky. Overall change risk is better for my shared library, because once it's compiled into the service I know it's going to work, and there's always a chance of not working at runtime. Better performance for sure, because now I'm not making a network call, it's an in-process call. Better at fault tolerance, because once it's there, I don't have to worry about network stuff affecting it. And way more scalable, because again, I'm not using any network resources to be able to call the thing. And so you look at this matrix and you go, well, count up the check marks, and looks like shared library wins. And that's the trap. We have services written in 4 different languages. Performance and fault tolerance are not a concern for us. We really want to manage frequent changes to shared functionality. The point of this is that not all of these matrix items have the same weight. And the heterogeneous code one here has a massive weight. And if that's true, then that just invalidates a whole bunch of these other ones. And so in this situation, because this is the actual trade-off that matters in this situation, this is why you can't do this one time and just decide once and for all, because there's always different factors that play into these trade-off analyses. This is a technique that we ended up using a lot in both our fundamentals book and our hard parts book, which is using qualitative analysis to iterate on design, which eventually leads you to quantitative analysis. What do I mean by that? I can't decide which distributed architecture style would be most appropriate for our new system, because you can implement pretty much any behavior in any architecture. It's really about how do they differ in terms of capabilities. One of the things that Mark and I did in our fundamentals book is create the star chart ratings between these different architecture styles, so we can get a kind of an apples to apples comparison between these things. This is qualitative analysis, because we didn't build every single piece of software in every one of these styles and measure them all, but we can tell by our experience that while we don't know microservices exactly how much more scalable it is than a layered monolith, it's a lot more scalable because it's a distributed architecture, because you can share load. And so this 5-star rating gives you about a 20% difference between each gradient. And what this allows us to do is get a more reasonable comparison between capabilities in these architectures and highlight the things that are real sweet spots in these particular architectures, which I've highlighted here. But now we go back to the business. What's important to the business here? It's about maintainability, testability, and deployability. When we limit it to just those and look across our architectures, it looks like microservices is the one that best supports those business goals in this particular situation. Because none of these is perfect, and what you're looking for is the guideline for what works best. We did the exact same thing for transactional sagas. I'm not sure which transactional saga to use for the new system. This is a situation where, as an architect, you go to your manager and say, "Manager, I've got good news and I've got bad news. The good news is we're going to have a perfect implementation. I guarantee the best possible implementation for the accounting workflow. The bad news is it's going to take me 8 times longer and 8 times more money than you allocated, because we're going to build it in all 8 ways, and then we'll measure them and see which one's best." Good luck with that. You need some way to filter these things down based on important criteria. And we did exactly the same thing with all these architecture sagas, distributed sagas, rated them depending on what their characteristics are like around coupling and complexity and responsiveness, et cetera. And you go back to the business, what are they really interested here, which is maintainability. We don't have maintainability here, but we do have complexity, which is a good driver for maintainability. Excuse me, I'm allergic to complexity, and it's a tough part of the talk for me to get through. But this shows us that this is a good candidate because it's the one that is the least complex and gives me the most desirable characteristics, and now I can actually measure those things. But once we've actually built the thing, we should do quantitative analysis, which is really measuring stuff. And that's really what evolutionary architecture is about. And I'm not going to spend any more time on this today, because that's what Rebecca is going to be talking about tomorrow morning, the co-author of Building Evolutionary Architectures. But this is about techniques and mechanisms to test these assumptions and wire them into your architecture once you're done with this idea of architectural fitness functions. Model relevant business use case scenarios to identify trade-offs. I don't know. Should we use a single payment service or a separate service for each payment type? That's a good question. The architects are down the hall arguing about what single means. That's not helping. So let's just model it. Single payment service versus individual ones around some common things we think we might do with it. Update credit card processing. What does that look like in both of them? Well, on the left, I have to update the credit card code and probably update the database and test everything because I've made a change. I want to make sure I didn't break it. On the right, I just changed credit card. I'm done. Decoupling for the win. Microservices are awesome. And so for the separate services, maintainability, testability, and deployability are much easier in that case. Scenario 2, add a new payment type. We want to add reward points as a payment type. Okay. We add reward points over here in my single service, which requires a change there and a change in the database, and probably have to test everything because we're making a change over there. Over on the right, hey, microservices, awesome. Add a new payment reward type, don't have to touch any of the others. Nice separation, decoupling, so extensibility much better for the separate services. Let's try one more. Use multiple types for payment. Over here on the left, piece of cake. They're all there together. It's all one service, transactionality. I can add it all up, make sure they all add up together. That's fantastic. Over here on the right, now I have to orchestrate across all of these different payment types and make sure that everything wraps up and is equal, which means now I have to do transactions across the database level, which of course we don't want to do, but we can if we really have to. And so separate here gives me a big hit on things like performance and data consistency, which is hard to deal with. So which one is better? Well, now we know what it depends on. Because we know what the business priority is maintainability, deployability, and testability. Which of these gives me better maintainability, testability, and deployability? It's the separate services. This is a great guideline because now we've both reconciled the business drivers for this, and now we know which difficult problems we're going to have to solve to be able to make that happen in terms of what the business really wants in our organization. And this is the answer to the question I posed way early on. This is very much an architecture level decision because of all the trade-offs associated with it. Maybe not all the way to architecture, but pretty close. And the last one here, avoid over-evangelizing a particular solution or technology because it always ends up biting you in the end. I did a keynote a few years ago called Why Does Yesterday's Best Practice Always Become Tomorrow's Anti-Pattern? Because it seems like that's always the life cycle of things like that. And here's the problem. You have a software architect that says, we should always use publish and subscribe broadcast messaging using topics because it supports extensibility and evolutionary architecture better. And here's why I'm ranting about this. If you have a system like this with individual queues and you decide to add a new consumer, now I have to add a new queue, I have to change the bidder, I have to add a new contract, all of which is a big hassle. If I'm just using topics to do that, I add a new consumer, register with that as a listener to that topic, no changes to the topic, no changes to the bidder, no changes to the contract. So this is why I love using topics as a way to do things. And everybody says, wow, you're right. That's what we should build everything with. And the narrator's voice comes on and says, meanwhile, a little while later, I can't create separate contracts for each one of these services, and now I'm doing stamp coupling. Every time I change this contract, 3 of my consumers breaks, and now I'm having to version these things and figure out who's getting them and how to reconcile that at the consumer level rather than the provider level. Oh, we just had a security breach because everyone has uncontrolled access to everything in that contract because everybody gets the same thing every time. Oh, and it turns out that some of these consumers have a lot higher scale than the others, so we want to be able to use queue depth to track auto-scaling, but you can't because it's a topic, it's not a queue. And so now we can't use auto-scaling because we don't have access to queue depth because it's a topic, not a queue. This is the outcome of over-evangelization. But this is a great indicator of what I was talking about before. Your job as the architect is not find magic solutions to problems and evangelize them because even if they're right in the short term, they're probably going to come back to bite you in the long term. And that's not really your best value to your organization, to become an evangelist for some approach. Your best job as a software architect, in fact, the decision makers in your organization need somebody they can go to and get the real information, objective trade-offs about what is this versus what is that. And that's really the essence of software architecture and the good role of software architects. That plus this ability to iterate on design, build an ecosystem that allows you to make decisions in architecture and then iterate on that. Maybe qualitatively to begin with, but then eventually quantitatively. This is the real secret to getting agile and architecture to work together along with things like design. Thank you very much for coming. Hope you enjoyed it. Thanks.